Good morning. Thank you for coming. I get the dubious pleasure of chairing the first session in the morning, which is, good because it gets it out of the way, but bad because we're always running that, that balance of waiting for a couple more people from the night before and trying to get started on time. I think we're going to be able to do pretty well though. We've got 3 speakers up this morning, although as we'll see as we go through, 2 of them are here in person. One of them is going to present from afar. So first up, we've got Tony Hain from Hain Global Consulting producing aBitCool. Next, we've got Augustin from Apnic, talking about determining Latin America and Caribbean internet connectivity. And then third, we have Jeff Houston talking about what's so special about 512. And that's certainly going to be interesting. So if I could welcome Tony to the stage, and we'll get his presentation up. Have we got any housekeeping this morning? No housekeeping? Okay, cool. Thank you, Tony.
Good morning. I trust everyone's awake. I'm not sure I am. So we'll try to get through this. So the project I'm going to be talking about this morning is called aBitCool Ignite. The group I've got a contract with right now in Beijing has started on a project to reinvent the ISP. As you might imagine, when you've got a limited number of incumbent carriers that feel no motivation for competitive, allowing people to be engaged and deploying new technologies, it gets very frustrating. And in this part of the world in particular, the number of carriers is generally limited. The number of choices, if you get choices at all, tends to keep you from thinking longer term and planning great things. So this particular project was born out of this frustration. We'll spend a little bit of time on the project goals, kind of what the deployment plans are. I'll talk about some of the challenges, in particular, try to highlight the ones that I think are going to collide with some Apnic policies as we move along. And then a little bit of status and wrap up. So again, this is a project born out of frustration. So like many of the ISPs of the early 90s, a bunch of guys got together, decided, if we were going to build a network, what network would we want? And they're building the network that they want. They'll worry about commercial success and feasibility as they go along, make sure that things work the way they want and are supportable. But the initial rollout is, by and large, exactly the same thing they were 25, 30 years ago. A few guys getting together, figuring out what they want a network to be, and then building it. But they're not just doing it for, a toy network. They're actually thinking this through and trying to reinvent and transform what deployment models look like by recognizing that consumer empowerment is, how you achieve true revolution. They're trying to rip out all of the incumbent infrastructure, decentralize things in a very dramatic way, and open up the edge. They really want an ecosystem to grow at the edge. So 21VNet is the hosting entity for this project. They run large data centers in China. And you'll notice the first thing they're doing here is disrupting their own business. Take the data center as you know it and throw it out. Start over. If everything else in the world is being decentralized, why not the data center? Why do we have hubs of data that we have to get high cost bandwidth to get connected to? Why don't we move the data out closer to the people? So the first thing you do is say, well, if I'm going to have access nodes that are going to be in the home, I've got resources there. If I just throw a little storage on it, I can actually start distributing data. This is nothing new. This is really just a reincarnation of BitTorrent, if you think about it. It's just centrally managed. Another piece of what they're trying to do is open up the edge. If you have to lease circuits to an exchange point, that's expensive. But what if there's no exchange point to connect to? You can't innovate. You're restricted to what the carriers allow you to do. So they're trying to say, let's redesign the edge and make it open. And while they're at it, since we're distributing the data center and throwing the whole thing out, why aren't we doing this as a national scale exchange point? Why are we having exchange points in data centers? We don't have a data center anymore, we just threw it out. So we're doing a national scale exchange point. This allows for permission-free innovation. You don't have to ask a carrier to allow ports through. And then, just to top it all off, watching what Google Fiber is doing and saying, well, that's nice, but, let's take it up a notch. The unit of bandwidth for subscribers is a lambda. You can't get anything less. If you need more than what you can get out of one lambda, you get 2 lambdas. This will have a fundamental change in the kinds of applications that can be deployed. If you look back in time, and granted, some of this is just looking back and deriving what happened as opposed to this was obviously a plan, but there's been a roughly 20x multiple of capacity that is commercially available to consumers over the last 30 years. And that is imposed pretty much through tariff, policy, access, and a general model of selling scarcity. The carriers have been in the business of not letting you have what you want and then charging you extra if you try to get it. They looked at what Google Fiber was doing and said, that's a nice start, but let's go for 10 gig or higher. If you think about what that does, it suddenly throws that 20x multiple out the window, and your limitations of growth of applications, as you see here in the bottom, we grew out of text and into video kind of over time, but now we're talking about very high capacity video, interactive, within communities, 4K, 8K higher kinds of image rates. That requires vastly more capacity than you can get from the carriers today. So how does this all look when you put it all together? Well, you start with the center of a national exchange point, for lack of a better description. And a lot of people throw up their hands and go, layer 2 broadcast domain, national scale has been done before, collapsed. Well, yes, that was old technology. If you come into it and approach it with the understanding of the failures of the past, you can revisit what needs to happen here. So there will still be data centers because there will still be people who have large volumes of video that they want to distribute, and they want to host that for control reasons. Not because they need to for data distribution reasons, but just because they want to have control over it. So those will be shown here in the upper right. You've got the traditional carriers you have to connect to. And then you've got all the subscribers out there on their own lambdas, kind of as you go along. And it doesn't really look all that much different than an existing topology. The big difference is where the BGP speakers are and how many of them there are. In a traditional, what we call the internet today, there's a small number of service providers, in a relative sense, that are allowed to participate in this game we call BGP. If you say every apartment complex manager is a service provider, you now have millions of BGP speakers. Jeff's going to be talking about the magic of 512 in a little while. 512 is so tiny in comparison to where we're going with this project. And it does have a vast impact on policy. A lot of the policies would not allow these organizations to become BGP speakers. And that is imposed by a historical old boys club mindset that says, we are in control, this is the way the game is played, play it our way. This project is trying to be disruptive. It's coming in and saying, the world as it needs to be is more open at the edge, and it will cause all kinds of issues, both in terms of technology and policy, as this region grapples with these changes. A part of the reason that I'm here today to speak about this project is because the team at 21 ViaNet said, this is not a problem unique to China. This problem exists throughout the AP region. And we want people to see what we're doing, see if there are pieces of this that they can take home and clone on their own. All right, and revisit what it means to be an ISP, what it means to be innovative at the edge, and then come back and as a collective worry about the issues in terms of how do you do neighbor discovery on a scale of millions on a single broadcast domain? There will have to be technology developments made. We may need to go back and revisit. 20 years ago, there was a neighbor discovery system built for ATM networks called the Mars server. Something akin to that may have to exist to allow these BGP speakers to find each other when you've got millions of them trying to do neighbor discovery across a broadcast domain. At the end of the day, it's not really that much different than any other network. It's composed of all the logical blocks. You've got members on the edge. You've got a switching fabric in the middle, which this particular case happens to be running layer 2 instead of layer 3. You've got some layer 3 transits at the edge, and you've got content providers. Nothing really different. It's just a matter of how it's organized, where the control points are, and who's in charge of making decisions. That's the real fundamental difference. It's taking the carriers out of the position of being the ones making the decision and pushing that decision-making to the edge. I don't know how widespread the information is about this, but there are frequent, quotes, peering wars in North America where the large transit providers start arguing with each other and decide to drop their peer relationship because they're not getting paid correctly, which causes all kinds of disconnection and rerouting and essentially failure from the endpoint perspective. There's also some things going on between Netflix and the access providers as to how you do compensation for delivering all those bits. All of those peering wars go away when the edge is free to contract directly and peer with whatever service provider they want and get content however that happens to work out. So this is trying to seriously disrupt telecommunications management as we know it. Now, as you might imagine, a dramatic shift like this is a bit much for some people to swallow. So by design, all members are type A members. But when you tell them they have to step up and speak BGP, they suddenly decide they want a more traditional thing. So we have a few Type B members who have decided that, I really don't want to get into that mode just yet. So there is support for a Type B member, but there aren't very many of those, and there's not intended to be many. It's more of a learning curve spot to park you while you get up to speed on how to do BGP correctly. That said, it's not a turn over the keys and let a million new members suddenly speak BGP that have never done it before. There's going to be some centralized hand-holding, templates, and infrastructure built out so that it won't be as wild and free as it could have been. If you are either really willing to subscribe to a lot of lambdas or happen to be the only one in a community, you will be connected with dark fiber. Otherwise, it's CWDM. And at this point, with this round of equipment we've got, it's 8 members on a line card. So it's not going to scale dramatically in this first round. But the expectation is that it will grow as we move along, and the scaling will be managed so that the unit of connection is a lambda. What equipment goes on that lambda? Right now it's GigE because that's the most economical. If you want 10 gig, that's not a problem. Due to existing policies in China, you cannot get BGP with the big carriers unless you're a big carrier. So all the members are having a problem getting transit access at this point. So they're having to peer and become transit members. So it looks in this initial round of deployment exactly like an existing ISP where you're subscribing to transit. But that's not the design goal. That's a point in time implementation detail to bootstrap the process, to go through and start revisiting who are the transit providers, where are they, how do we get access to them, and for the incumbents that refuse to do BGP with the smaller entities, a way to get around them. This may become an issue in other parts of the region if you're trying to do the same kind of thing. You may have to establish a transit provider for the bootstrap process. This is not a design goal, like I said, it's just reality. A massive change requires incremental steps which are not exactly on the path where you want to go, but you take them just to move one step forward. So as I started this discussion, I said, revisiting the data center. If you take the data center and fragment it across all of your members and distribute it around the edge, it's still a data center. But you can do smarter content caching. You can actually push it closer to the people who are asking for it in real time. And if you do mechanisms like BitTorrent, where thousands of nodes are hosting parts of the content, it's accessible all the time and in pieces and parts wherever it needs to be. This first round of equipment prototypes are Intel-based equipment running OpenWRT. They are built with 4 WAN ports by default. So that allows for growth in the WAN space, and if you happen to have some other entity that came up and decided they wanted to do a similar kind of thing in parallel, there's no restriction. It's an open edge. Here's the equipment connected to this network. It's part of the data center. If you've got another provider, connect. Go for it. Up to 4 providers. It also has 3 Wi-Fi radios and mesh technology built in, so it's capable of fairly extensive networking in its own right. But this is the edge. right? How you grow beyond that and redefining what that home network looks like is another piece of the problem. Getting all of the data pushed out and getting it, in a peer-to-peer content cache model is going to take a little time. This first round of routers is primarily doing access and bootstrapping the content distribution piece. Once the content distribution piece is kind of going, then you've got to have something to consume the content. And they took a look at what was going on with Chromecast, and they said, that's really cool, but it's closed. So what if we work with Firefox and open that up? So they've been in process of building a dongle for essentially the same functionality as Chromecast, but it's open. It was supposed to have been announced in some grand announcement last week, and it didn't happen, but we're still going to talk about it here. So you're hearing about it, but it's not officially available yet. At any rate, it's partially software compatible. I actually controlled one with my Chromecast app one day. So I have a Chromecast at home, and I had the app installed, and I just, on the Wi-Fi, fired up and started controlling their widget. Now, it doesn't have access to the same content because getting the keys to decrypt is part of the closedness of Chromecast. So there are things that it can't do just by the nature of intellectual property rights, but from the technology perspective, it's there and works the same way. And they look at that as a building block for decentralizing content consumption. We've got content storage decentralized. Why don't we push this out even further and have more high bandwidth devices, so you can take older screens that are not capable of direct internet streaming and fire them up, and now you have much more content consumption. As I said, we have to rethink what the home network looks like. It's not just a simple flat single LAN. That's what everybody assumes a home network looks like. If you go talk to app developers, they assume the home network is a flat LAN. They can just do broadcast and everything is on the same segment. Chromecast is a bad example of exactly this problem. If you're not on the same segment as the Chromecast, you can't find it. You're not allowed to put in a name. You're not allowed to put in an address. It assumes it's on the same segment. Many of the Internet of Things devices are going to be limited UI. They're going to have to be controllable from off subnet. As you get more and more kinds of things connected, you want to start doing isolation the same way any enterprise would want to do isolation. Now, this particular network happens to be mine. It's not that mine is a good example. It's just mine was the one that was documented. And they wanted to, display what home networks, they would like to look at and talk about. And I happen to have a documented network. So that's what this one is. Now, it will be slightly different when I get home. There's going to be another Chromecast in there. But at any rate, the point is you've got lots of kinds of functions, and you're trying to split those up and isolate them the same way any enterprise would. How this gets automated is one of the things the IETF has been struggling with for a long time. And in some ways, I've considered that whole effort misguided because it's being driven by a bunch of geeks who think like managing networks, right? And think in terms of being in charge and managing instead of thinking in terms of automation and plug and play. It takes a very different mindset to assume no knowledge and things just plug in and work than it does to think in terms of, I'm a manager, I know how things should work, I want it to work the way I want it to work. That's why the IETF struggles. At any rate, new technologies are coming along, and for those who haven't seen them yet, they wanted me to point out there's actually a treadmill connected to this network. Why is a treadmill connected to the network, you might ask? Well, it happens to have an Android tablet built in, and it goes off to Google Maps and knows the topology. So you pick up a location in Google Maps and start walking. Hill goes up, incline goes up. Hill goes down, incline goes down. And you're watching the Google Street View images as you walk or run or whatever you're doing, right? So the technology is evolving. People are finding new ways to do things because they can. And if we allow even more openness at the edge, even more of those kinds of things will happen. So what are the successes? We're not pushing the edge of technology that hard, so equipment is working as expected, right? Minor failures, but it's happening. Now, I was supposed to get real numbers, and there was a crisis, so the people who had the real numbers didn't come today, so I don't know what the numbers are. But they are deploying, it is happening. Challenges. This is a major, major mindset shift. Getting the entire team on board with the vision is one of the biggest challenges, right? The CEO and his leadership team have a vision. It's very different from what the implementers are used to. And they keep implementing in traditional modes, getting them to rethink and understand, no, this is different. It really is different. We're not just saying it's different, it really is different. Getting that part of the problem dealt with is a big piece of the challenge. Getting permission to deploy fiber. That's going to be a problem everywhere all the time. It was understood to be a problem, but it is a problem. You know, it's one of the challenges that exists. It's not to say it's easy, not to say it's extremely hard. It's just one of the things that's in the list you have to worry about. Because you've got this problem with getting the vision implemented, everything tends to go slow. So while there was this hope that we would be well along by this time, it's very slow. I guess this is the simplest way to put it. And this organization collective is going to have a very unusual relationship with Apnic. Millions of new members with a very different expectation set. Right? They don't need vast amounts of address space. They need an AS and their own block. Right? By itself, that shouldn't be a problem. But their size is so small and their numbers are so vast, they will change policy here over time because they outnumber the historical members. So, as I said, deployments are happening, pictures of real things going on. Speed tests show they're getting, in the gig range without too much effort. Overall, exactly what you would expect. Push the edge of technology, just don't push it too hard. And that should have stayed on the question slide, but it didn't. I don't know why it's not staying there. Anyway.
In lieu of the slide, are there any questions?
It's too early in the morning.
It is certainly too early in the morning, but one question.
Hi, Mark Smith from Next Gen Networks. That's very,
Wasn't as weird as it looked.
Yeah. I'm just a bit curious of the sorts of organisations that are participating on the low scale. Profiles of them, are they small and medium enterprises? Is this their typical business, or are you seeing a lot of new village telcos or small, mum and pop sort of style things?
Yeah, the first bunch are the serious geeks who have enough money to pull fiber off to their own house, right? But beyond that set, there are the small business video content, gaming content houses that can't get into traditional data centers cost effectively. That's the initial set of real customers in this. And then as it moves forward, there's focusing on apartment managers and saying, you can become a service provider for your apartment complex and boost the value of your complex, as opposed to going off and trying, so it's trying to revisit scale and say, yes, it's not every individual, but it's an apartment manager who's got a few hundred,
the small amount of
few hundred customers at the edge, right? That's the target after the content round.
Okay, interesting. Thanks.
Cool. Thank you. We've got another question from the floor.
Tony, George from Apnic. The New Zealand national fibre rollout had a fairly interesting economic model that said we can use a rolling capital fund to build the deployment. We build an area, we achieve market, we get cash coming back in, that cash then is used to project forward. And it seemed to work for them, but they are a very small economy, and so they've got all of those issues about economies of scale. Sorry, Dean, compared to China.
I'm a very big economy.
Compared to China. So I wondered, given that this is kind of national scale infrastructure, utility, pits and poles for the physicals, and then let's have competition in the upper layer, are you having to think about that kind of capital structure to actually get the money? Because people who buy these things tend to want to see their cash back. So
yeah, so there is a piece of that. The organization that's funding this is less concerned about short-term return.
Great, so it's the long-term investment perspective.
They are long-term investors, and it is going to be rolled out on a city basis to deal with, just the process and getting that initial set of customers. And you don't go national immediately. You start in Beijing, and then you move to Shanghai, and then you move to Hong Kong, and it will do the rolling piece, but it's designed up front to be.
It's nice to hear about people thinking about utility timescale return on investment, because that's what built out the copper. So I think that's really great, personally. Am I allowed another?
One more question, as long as it doesn't call New Zealand small.
So,
New Zealand is smaller than Beijing. We can
I know, economically small. So again,
but our rugby team.
But you're bigger than Seattle.
In the NIRSIG, we had a very interesting presentation from CNIC, who talked about how the China petrochemicals industry sees Internet of Things as something they want for their own internal purposes. They've got a huge deployed network of measurement devices, gates, controllers, valves that they want to put under this framework. Someone else mentioned that they're doing citywide CCTV, less socially appropriate for me perhaps, but nonetheless they're interested in V6 and IoT for that kind of thing. So it feels like there's a background that this is a thing in China. So when you say you're talking about doing it in the domestic context, that's not completely naively unaware of that, is it?
No, and in fact, as I said, they want other organizations in this region to understand, because they think many people have the same issues. And I actually want them to be extremely successful, so I can take it back to the FCC in the US and say, you could have this if you didn't have such stupid regulations.
Yeah. By the way, I'm a Chromecast owner, so I like them.
Yeah.
Awesome.
Kenny Wang, Apnic EC. Two questions. The first question is, you put BGP to the edge, and I couldn't see the value of pushing BGP to the edge, because if architecture-wise, this can be done through the other protocol. And second question is, all the content was delivered from the edge as well. It seems against the trend to put everything content to the cloud. So can you explain? Thank you.
Okay, so yes, other protocols could be used. They are overly focused in some ways on pushing BGP to the edge in terms of making it a very distinct policy statement. BGP is a policy engine, not a protocol. It happens to be a protocol, but it's a policy statement. And that's the focus on BGP is policy is pushed to the edge. Now, you can use all kinds of other protocols and implement the same policy, but their focus is on that to say, we're pushing policy to the edge. Our implementation is going to be BGP because that's the way traditional ISPs think about policy, right? I lost the other question.
Second question is the content delivered from the edge as well. So it seems against the trend.
Well, so it's a pendulum. Think back 10 years, and BitTorrent was a big deal. People were pushing content from the edge. It swung to the center. And now there's all kinds of exposure issues, from the Snowden leaks. So there's this impetus to push it back to the edge so that it's harder to track. It will come back to the center. It did. It was in the center in the 80s. It moved to the edge, moved to the center, moved to the edge. It's
the great circle of life.
Yes, I mean everyone wants control of the content because they perceive that's where the value is, and so you push the content to where you want the value to be.
Awesome. Well, thank you very much. Our next speaker is going to be, presenting remotely. We've got the slide deck and, well... It's a slide pack, it's not remote. There you go. It's a slide pack. So, Augustine from Apnic, and the slide pack is on determining Latin America and Caribbean internet connectivity. So, we'll start that now.
Hello, my name is Agustin Formoso. I work at Apnic as a software developer, and we'd like to share with you a side project we have. It's called Simon, and it determines network connectivity through latency measurements. The project tries to address a real problem that presents lack region internet, that is poor connectivity. Suboptimal routing is a cause of poor connectivity, and what we do is determine suboptimal routing through latency measurements. The problem is that most of the traffic that travels within Latin America gets routed outside Latin America. This affects domestic traffic quality and impacts the fees end users pay for it. The project's main objective is to provide recent and accessible information about the latency measurements done in the region for anyone interested in making diagnosis to regional internet providers wanting to check their network, and even researchers who want this data to draw any network conclusions they can get to. But the data on its own, it's not a goal. The goal here is to make network operators do better agreements between them, or encouraging them to join a local internet exchange point. The project started at about 2007 with some talks at a regional connectivity group. At about 2009, the Java applet was released, and what it does is some NTP latency measurements. this group is not only integrated by Apnic, but also it has some other groups from being represented from the region as internet exchange points, content providers, people related to internet infrastructure. That makes that the project has many sides. One of the main project deliverables is a latency country matrix. What it does is it charts all the gathered data.
What we're going to do is just stop that for a second. We're pretty sure we know where the echo/reverb/disco is coming from. And these guys are going to quickly adjust that. Then we can get the volume up a little bit. It is a little bit early in the morning, and I don't want the low reverb putting all you guys to sleep. So we'll just take a couple of seconds. This is normally the time when I dance on stage. I'm going to save you from that as well. Yeah, so pretty much, yeah, a round of applause. A round of applause to me not dancing. That's great. I don't think we can fit in a Jeff presentation in the minute that they assure me it's going to take, so I don't think that's worth it.
I work at Apnic as a software developer, and we'd like to share with you a side project
There we go.
we have. It's called Simon, and it determines network connectivity through latency measurements. The project tries to address a real problem that presents lack region internet, that is poor connectivity. Suboptimal routing is a cause of poor connectivity, and what we do is determine suboptimal routing through latency measurements. The problem is that most of the traffic that travels within Latin America gets routed outside Latin America. This affects domestic traffic quality and impacts the fees end users pay for it. The project's main objective is to provide recent and accessible information about the latency measurements done in the region for anyone interested in making diagnosis to regional internet providers wanting to check their network, and even researchers who want this data to draw any network conclusions they can get to. But the data on its own, it's not a goal. The goal here is to make network operators do better agreements between them, or encouraging them to join a local internet exchange point. The project started at about 2007 with some talks at regional connectivity group. At about 2009, Java applet was released, and what it does is some NTP latency measurements. This group is not only integrated by Apnic, but also it has some other groups from being represented from the region as internet exchange points, content providers, people related to internet infrastructure. That makes that the project has many sides. One of the main project deliverables is a latency country matrix. What it does is it charts all the gathered data, but sorted by country, where originating countries are vertically and country of destination is horizontally. The matrix is very simple, but it provides an instant picture of the regional connectivity. You can clearly see that there are some countries that have poorer latency values than the rest. Examples are Dominican Republic or Paraguay. The matrix also has a clear lower value for its main diagonal. That main diagonal is the in-country latency measurements that were done. So naturally, those measurements should be lower than the rest of the matrix. Taking the main diagonal and making a ranking of the sort of top 3 and worst 3 performers, we can see that the best 3 performers had about a 50 millisecond latency within the country, whereas the worst 3 had about more than 3 times the latency of the best ones. We also have a latency matrix for autonomous systems. This matrix is much smaller than the country matrix because we filtered the data that is being charted to those ASs that have originating and destined measures. That is, for all of the ASs charted, someone has done a measurement from or a measurement to that AS. At the moment, we're looking for a better latency measurement tools. The Java applet has been around for a while, some years, but we're looking for some tools that allow us to get much more data than we're actually getting from the applet. The applet is a component that requires user intervention. And one of the main motivations behind JavaScript is that you can program automatic scripts to run in background, for example, when a web page is loaded. JavaScript runs on browsers, and it can access many resources that are already there in the internet. Currently, we are pinging some speed test sites as well as some other sites that respond to HTTP GET. What we do is use the already there user internet traffic and make it do the tests with like in the background without the user even noticing it. With JavaScript, we can reach many more users, many more sites, not only the NTP servers that the applet reached. As it has no clicks required, we can trigger it in an automatic background fashion, and it's configurable in order for those in charge of maintaining web pages can configure what percentage of the traffic is doing the tests and how many tests each user is doing. You can configure the test in order to increase the amount of users that run tests through the time. What we were looking for when developing our own JavaScript tester was, on the one hand, having the ability to run automatically and in background scripts as JavaScript does, and on the other hand, being able to run tests from one client to several servers, as non-JavaScript testers do. When exploring for some already done JavaScript latency measurement, we found Yahoo Boomerang. But the only problem it had is that they actually don't do one-to-many tests. They only test the client-server link. So we decided the best option was to develop our own JavaScript client that would ping from one browser to several web servers. In order to determine what JavaScript is actually measuring, we had to explore a little bit how the TCP and JavaScript relationship is like. When you're actually doing an HTTP GET through JavaScript, after the TCP handshake, after the TCP connection establishment, what actually is happening are some push and acknowledge dialogue between client and server. So making some assumptions that the server has a pretty good performance and it's not very loaded. In the picture, we're talking about D1 and D2 tending to 0. If those conditions are met, then we could say that the time difference between T1 and T0 tends to be the RTT between the push and the acknowledge received by the client. when determining the relationship between TCP and JavaScript latency, that is, when doing some latency measurements in the JavaScript in the browser and sniffing that traffic at the TCP layer, we found some consistent differences. First of all, the data for TCP, that is the green chart, is almost always centered, and the data for JavaScript is always right-tailed. There's also a shift in the latency values at the JavaScript layer. Let's say the browser always introduces a delay in the TCP latency. We're doing extensive testing in order to parameterize those parameters and try to map it with which browser has run the test. What we're looking for is if those differences can be corresponded with the JavaScript engine implementation that each browser has. What we do then is, after receiving the JavaScript data, we should transform it into a TCP data, knowing which browser and which operating system has executed the JavaScript file. Some tests, some quick tests we have run with 3 different browsers on the same operating system at the same time showed us that the browser implementation actually changes the way the JavaScript code is run. So we can see that the blue histogram is clearly different from the red or from the green one. What we are trying to do is reaching a table of this kind where we set a fixed browser, let's say the blue browser, as a reference, and then we take note of the difference from the red and the green browsers and try to establish a mean difference and a standard deviation difference in order for us to later compare and have all the data from the different browsers in the same database. We have found some problems we simply could not address. The first one is related to tabs, windows, and even desktops entering power saving mode. That is, the JavaScript code is just sort of frozen and latency measurements start timeout. What we do is just dropping those samples and, well, hoping the user to go to that tab again. What we could do is just allowing very, very few samples to be taken in order to have enough time for the user not to visit another tab or another window in that browser. Another problem affecting latency measurements were congested LANs and wireless. We did some quick and dirty pings with wired in red and wireless in blue, and what we found out was that no clear difference in its mean value was seen. Wireless has always been a difficult topic to address, and we would like anyone who has experimented with JavaScript and wireless and can give us some feedback on their experience would be much appreciated in order for us to get that input and well, try to make some adjustments in the measurements. From all the data gathered, we could draw some conclusions. The first one is a case between two neighboring countries, Uruguay and Argentina. And you can see that latency between these two countries has 2 kinds of behavior. Part of the traffic is going through a sub-100 millisecond round-trip times, whereas other part of the traffic is going through a 200 milliseconds RTT. We don't know what the cost of this is, but our main objective is to provide the data to network operators in order for them to check if their networks are being part of the over 200 millisecond traffic, and try to address those problems in their network configurations, or just evaluate if they should do some peering agreements with other network operators. Another case we found is the one between Uruguay and Brazil. Just as the case before, latency between these two countries has no unique behavior. It is centered mainly in 3 points. The bad thing about this case is that the worst performing latency mean is the one holding the most of the measurements. That is, the traffic measured between these two countries could be seriously improved by shifting down the worst performing load down to 100 milliseconds, let's say.
Well, regarding the JavaScript tester, what we could say is that it enables us to have lots of test points and lots of testers. This makes our database grow much more than it did with the NTP measurements, and may enrich our database a lot. Some assumptions were made in order to get to the conclusions we showed. One of them was that JavaScript results show a log normal distribution. That was actually a conclusion that we reached as a rule of thumb, but we'd like to make some rigorous distribution testing in order to know which distribution best describes the JavaScript latency behavior. We also would like to do some more statistics regarding autonomous systems, and also build the table we talked about how JavaScript delays regarding TCP latency is corresponded with browsers' implementation of the JavaScript engine and the operating system under which the browser is running. We're also looking for another data sources that may be out there and may enrich our database a lot. I'd like to give some special thanks to the Apnic software development team and Kai Archipelago project, who provided us with some very meaningful data that complemented the one we already had at the project. And that's all. Thank you for watching, and we invite you to check the site, and if you have any comments, you can write to my personal address, or you can write directly to our Twitter account. The code is available for everyone who's interested to use it, copy it, and making it even better. And well, we're looking for some feedback of your part. Thank you very much.
Okay, thank you. So we do have a couple of other Apnic members at the meeting. Are they in the room at the moment? If they are in the room, maybe we can take questions directed at them. If not, what I'll do is give people an opportunity to, if they've got any comments or feedback, to state it at the microphone so that it's recorded, and then we can go on. So, no to the Apnic people. All right. Does anyone have any feedback on the project? Any comments that they'd like to make? No? Okay, well then, a big round of applause. And without further ado, I would like to hand over to Jeff.
Good morning all. That's twice the number of people from yesterday at 9 o'clock. Well done all. It is amazing. Yes, good morning all. This is a timely presentation about routing. So the 12th of August this year, a memorable date, it's my middle son's birthday. But as well as that, as I'm sure you all know, it was World Elephant Day. Yep. And evidently some spacecraft called Rosetta is closing in on a comet, which is amazing stuff. and there were triplets of pandas born in China, and you know, it was really just another day, right? 12th of August, except that that day, according to the Telegraph in the UK, according to the Wall Street Journal, according to the Washington Post, and even according to that rag published by Rupert Murdoch, the internet collapsed and died, which you might not have noticed, but you know, the press is just right onto it. But you know, the headlines were certainly dramatic, that the internet came down to a slow crawl, major sites had problems, it all broke, blah, 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 death of the internet, news at 11. What happened? I'm like, was this a case that we'd all been sitting in this cold room and the air conditioning was going full blast on the 11th and, you know, we all sneezed at once on Tuesday morning? Was this kind of some collective insanity that we sort of broke the entire internet all at once? And when you look hard at the routing system, you might be tempted to believe that. This is a snapshot of every last update received by a default-free BGP speaker that I run for that 24-hour period. Now, BGP has little messages, and those little messages come in two types. Here is an announcement for a prefix that you can now reach, or it's a revision of an announcement. It's basically saying, here's a prefix and you can now get to it through me, says the peer to use. That's an update, an announcement. And there's another kind of protocol message that BGP receives, which is, if you were using me to get to that prefix, don't use me anymore. That's a withdrawal. So I can no longer reach 1.1.1.1/24, use someone else or forget about it. So I record all these like a gigantic tape recorder, and then you actually look at what were the updates and what were the withdrawals, and what was the net result in the routing table. Because every update that's new causes you to add one to the routing table, every withdrawal is a -1. And so at midnight, you know, standard stuff. BGP is amazingly quiet. I'll get back to that, Tony, because there's a message there. BGP is amazingly quiet most of the time until 7:58 in the morning UTC. Someone decided to announce 22,000 routes in the space of about 2 minutes. BGP is really efficient, really efficient. So that announcement spun around the world inside 80 seconds, and certainly here in Brisbane where this router is located, it saw it too, 22,000 routes. Obviously someone made a mistake, because within about 90 odd seconds, those same 22,000 routes were withdrawn, hence the massive spike upwards and the massive spike downwards. And then the rest of the day, a few announcements, a few withdrawals, and as you see from the brown line sort of slowly getting above zero, the network kind of grew a little bit for the day by the end of the day. So there were actually 2 events that day which were kind of interesting. The finger trouble was our dear friends at Verizon, who decided they'd test the world by sending out 22,000 more specifics, thank you very much, and then deciding, oops, they didn't mean it, and they really didn't, and withdrawing them straight away. But as well as that, that kind of background blue line is just slowly growing. A few announcements, a few withdrawals, but the net growth rate tipped over 512K at just after midday UTC. Now, in a longer trend, that wasn't anything unusual. That's a week of BGP. And what you find is folk announce routes, folk withdraw, but there's this long, steady, slow growth in BGP. It's just a process. And, you know, for a few days before that, we were toying with 512, and then on Tuesday, it's sort of, bugger it. Let's just simply announce some routes. 600 new routes came in, and we just kept on growing. So why was that a problem? Anyone use Cisco Cat 6500s? Nobody. No, oh, one. Well done, you. They're cheap. And the reason why they're cheap is they're really old. That's 2 things about them. But the other thing about that is because they're really old, they have a few built-in limitations. And, you know, the print's really fine, and none of you can read it, but let me read it out for you. If you're using a CAT 65000, it has this very special type of memory, which we will talk about later, called ternary content addressable memory. And if any of you did computer science, you'd go, aha, I remember that term vaguely. It's super duper memory, which is addressed by content, not by address, which for routers is really good stuff. So CAT 6500s use this kind of memory. It's expensive memory, so there's not a whole heap of it. And the fine print for the CAT 65000 says the default numbers for the blah, blah, blah from Cisco is 512K IPv4 routes and 256K of IPv6 routes. Now, this is 10-year-old equipment. At the time, both of those numbers were well in excess of what you'd think the internet was going to get to. Because if I go back to 1999, the size of the internet table was about 50,000. So, 512K, whoa, overkill. 256K of V6, whoa, even today that's overkill. But on the 12th of August, that number wasn't big enough anymore. Aha, I don't run Cisco, I run Brocade. Well, if you had a NetIron XMR, it also has a content addressable memory, and by default, fine print down the bottom, the default size of the NetIron XMR blah, blah, blah is 512K. Again, it's pretty old equipment. And, old is cheap, so we keep on using it. And this is not the only equipment around there that has these kinds of limits. So that's why certain parts of the internet that were using this kind of equipment fell over. Now, what was the problem? Was it just the 701 leak, that massive spike that was an blur? Probably not. Although, a lot of operators do the max prefix guard in their BGP config. You're my peer, you can only send me a maximum of 500,000 routes, any more than that, and I'm going to shut down the session. Now, if you did that today, that's a stupid idea because I'm going to send you 512,000 routes, you're going to shut down the session, this is not going to work. So typically what you might do is set a limit of, say, 700,000. So if you leak a huge number of routes at me, I will shut down the session. I set this up, I go back to sleep, I go and do other things for the next few years, the routing table gets above 700,000, our peering session breaks. Whoops. Once you start doing this kind of thing, you have to constantly look at your configurations. So the first thing is, was it the 701 leak? I don't think so. But I think it was really that inexorable growth of the internet that passed 512K. So this should not have been a surprise to anyone. This is the history of routing for 20 years. And these are snapshots taken every hour. So there's an awful lot of dots on that screen. GNU Plot had a huge amount of fun plotting it. And oddly enough, you can actually see a huge amount of sort of business events that happened in the last 20 years. The 1994 introduction of classless interdomain routing, the great internet boom or bust of 2001, the actual growth, the real growth of the internet in broadband DSL modems through the mid-noughties. Even the global financial crisis actually slowed down growth around 2009. And you actually saw the amount of capital growing the internet was actually pulled out. Fascinatingly, address exhaustion went unnoticed. He just kept on adding more routes. Bizarre. This is the last couple of years of the V4 routing table. It actually crosses over address exhaustion in April 2011. And, when you try and curve fit that 3-year line, you end up with something that's pretty linear. Even if you try and do an exponential fit, it's not a very natural fit. So the prefix count across the last 3 years has actually been inevitable. We were always going to pass 512K routes, and even 3 years ago, you and I could have confidently predicted it was going to happen in the middle of 2014. So for anyone to claim on the 13th of August, oops, what a surprise that was, they had their head firmly stuck in a barrel load of sand, because this was just blindingly obvious for anyone who happened to look. Those are the kind of big stats of the internet over the last year or so. I don't know how long you've been looking at these kinds of numbers, but 10, 15 years ago, the internet was doubling in size every 3 months, doubling in size every year, phenomenal growth. The world's population grows at what, about 2 to 3% per year? And the internet's now growing at somewhere between sort of 7 and 10% per year. So it's sort of slightly above population, but it's not that much higher. A lot of these markets are saturating. And it's true, there are more internet devices than toothbrushes out there on this planet. But even so, the growth rates are now no longer dramatic. 10 to 12% is only slightly above, GDP in some sense. And so in some ways, the internet is growing at a relatively conservative rate. And it shouldn't really be any great cause for concern. In actual fact, growth is slowing. Why is growth slowing ever so slightly? Well, perhaps address exhaustion does have some impact. Perhaps the use of NATs in v4 is indeed slowing down the rate of advertisements. Perhaps the aBitCool process hasn't unleashed the awesome magic of 10 million new routes and 10 million new BGP speakers. Thank you, Tony. Or maybe the critical market sectors have actually been saturated. But even so, growth is slowing, not growing. What about V6, the great hope? This is the last few years in V6, and you can just see World IPv6 Day. That's that slight sort of bump in the middle of 2011. For the life of me, I can't see a year later IPv6 launch day. I just can't see it. Whatever impact that had in terms of signing on more people to run V6, it wasn't a lot of people. Where are we up to? About 20,000 routes. There are some up days, there are some down days, but about 20,000 routes. Growth rate's certainly higher than V4, certainly higher. And on average, 30 to 40% per year, which is still a lot. That's really, really very encouraging. In fact, I'd say more accurately, between 20 and 40%. If this persists, looking at the number of AS numbers, we'll be running an all IPv6 network by 2030. God, think of the NATs you're going to need by then. It's frightening. Something's impossible about that prediction. Either we've got to do more V6 a lot more quickly than we're doing now, or you guys are going to be running the NATs from hell by then, because there is no middle ground here. You're either going to run V4 well past its use-by date, or you're going to stop. My advice is stop, but that means a lot more V6 a lot faster. But I digress. Oddly enough, actually, the pace of V6 is slowing as well, and I'll show you some figures to show that. And I just don't quite understand why the pace of growth is slowing. Have we all got bored with the story? I don't quite understand that, but I'll show you some figures that actually illustrate that. But let's move from yesterday to tomorrow, because in using this principle that tomorrow is just a lot like today, right? Which is strictly the case. The sun gets up, you get up, have breakfast, have some coffee, contemplate the world, do whatever you want to do, much the same. And let's have a look at BGP using that technique. And what you do is you look at the recent past, do a curve fit, and then figure out how those curves run forward. So that's 10 years of BGP. Those are some curve fits. And it's kind of fascinating that the last few years have gone linear. There's kind of a bend to that curve, and you might think it's exponential, but the last few years, the best fits are linear. Remember maths? Yeah, some of you remember maths? Do you remember calculus? Leibniz, Newton, calculus. Do you remember first-order differentials? This is one of them. This is the rate of change, right? This is the first-order differential. And what it says is actually quite interesting. The BGP seems to grow at about 150 new entries a day, and it's pretty regular these days. You go, but Jeff, that's not slowing down. What if I talk about the percentage of change? The BGP network grows by X% new entries per year. Well, back in 2011, that was around 15%. These days, it's around 10%. And as you see there, using this sort of high and low bound plotting, thank you stock market analysts, you can actually see that in relative terms, V4 is slowing down. In relative terms, the pace of growth is actually coming off the boil. And we're kicking at around 10% per day. I can use those numbers and do some pretty confident predictions that if we keep on doing what we're doing, if we don't do the madness of unleashing millions of new BGP speakers, and we'll see why that's mad in a little while, Tony, I can actually tell you and tell your vendors what you should be buying. Because if you want equipment today to last until 2019, you better be able to cope with 750,000 routing entries. The level of uncertainty of that, pretty low, because the network is growing very, very stably at approximately 50,000 entries a year. So BGP4, looking okay. What about 6? Hard to say that it's linear. That's the last 10 years of 6. And, you know, World v6 Day notwithstanding, the last few years have been exciting. We've actually gone from a couple of thousand folk to 20,000, and it is growing, and it is growing like crazy. First order differential, this thing bounces, looks a lot better. The first order differential certainly is up there, 20–30% at times. In relative terms, not quite the same story. In relative terms, if I blow that up a bit and do some curve fitting, the pace of growth is coming off. Back in 2011, and I will give World v6 Day credit, relatively it really did make a huge difference. We almost doubled the routing table around that period, 100% relative growth rate in those couple of months. But since then, it went off the boil. It was kind of, oh, that's yesterday's news. And these days, the relative pace of growth is slowing. And that's not a good story. We need to do better than that. So from that respect, that's why I see the growth in V6 is actually coming off the boil a bit in relative terms. Even so, it's pretty easy to make some predictions, and I will do so using an exponential model because you've got to be optimistic, right? So we are going to grow, and it's probably inside those 5 years going to grow from the current sort of 20,000 entries to at least 120,000. I can't see it growing much more than that inside the current figures. Something has to change dramatically for those numbers to change. So we kind of then understand what we're looking at in terms of growth. Is that painful? What makes pain in technology? Why does stuff get cheaper? Why does stuff get more expensive? What's the constant? Because after all, chips are just processed sand, right? And if I can do something on a chip today and I can do something on a chip tomorrow, the cost should be relatively constant. Moore's law says something interesting. Moore's law says that the number of gates per square centimetre of chip doubles every approximate 18 months. And Moore did this back in the early 70s off almost no data, and the world has said, oh God, it's a law of physics, is it? We better not overachieve or underachieve, we better just stick to that trajectory. And so we've done so for the last 40 odd years. And most of the processes that we actually do stick to that kind of formula, the number of gates. And these days I think we're up to 3.9 billion gates on a Intel Pentium whatever processor, phenomenal number of gates, sticks to that same law. And what that says is, if your problem is in the number of gates, as long as the problem grows slower than doubling every 18 months, it'll get cheaper. It'll get cheaper to solve it because you just don't need as much silicon. So how does routing compare to Moore's law? Big yawn, huge yawn. Whatever BGP is doing in V4, Moore's law is not your problem. So in terms of the size of routing, I don't think routing's a problem. Yes, you need to keep on buying equipment from time to time. You can't run the internet on an IBM PC XT. Sorry, you know, what the hell. You need to buy current equipment, but the equipment that you're buying doesn't get more expensive per unit of routing. It gets cheaper, and that's good news. What about V6? Well, it's still growing, but it's still comfortably under Moore's law. So it's still basically a story that says this is not really a concern. These growth rates are modest, that's okay. Routing is not actually going to be a problem. Or not. Because it's not just the size, it's what you do with it. It's the updates in the protocol. And when I look at the updates in BGP, there's a really, really strange story. That purple line is the growth of the routing table. We've doubled over the last 8 years, yeah? From a little over 200,000 to a little over 500,000. But look at those lines at the bottom, the red line, the number of withdrawals per day. Weirdly, it's constant. How about the number of updates, the green? Well, it's grown a bit, but it hasn't grown a lot. This is weird. I don't know about you, but I drive a car to work. Maybe I'm naughty these days, but I do. And have you ever noticed that when there are more cars on the road, the trip gets slower? Right? You know, you just can't drive at the same speed anymore. There are more people in the way. This is weird because we've actually doubled the number of things in the routing table, yet its instability has remained constant. Whoa, whatever we're doing is brilliant. Whatever we're doing. But we don't know what we're doing. We don't understand why BGP scales. But what we do understand, Tony, is that when we break it, we'll know that it's broken. And then we might understand why it didn't break before that. So there is some funny dynamic in BGP that the convergence has been steady, rock steady, at 70 seconds since 2007. That's fantastic. This is like driving your car to work and the amount of traffic around you doubling, but it still takes the same amount of time. Somehow, we've managed to absorb an incredible amount of growth in the routing table, yet its dynamic performance is unaltered. We have some vague clue about this, that partially it's your behaviour. You hate being someone else's customer. Hate it. And what you try and do is connect as close as possible to tier ones, to exchange points, to try and bring your network as close as possible to what you think is some kind of core of the network. So over the last 20 odd years, the average AS path length in BGP has not got longer. It's like as we've grown, the radius of this star has remained constant and you've just increased the density. And for a distance vector protocol, that's a really, really good idea, because the time to converge is based on the diameter of the ball, not on the number of players. But we're still have no clue why the number of bad people, the red lines and the green lines, are constant. We have no idea what's going on there. But if that breaks, worry a lot. So if you think BGP is an infinite piece of plasticine that you can do anything you want and BGP will just scale, you're walking on ice, and we have no idea of its thickness. Totally walking on ice. And that's the real issue here about what's going on in BGP. What about V6? Well, V6, oddly enough, even though it's very, very small, has almost a similar dynamic. Look at that red line at the bottom. As the table grows, the number of withdrawals is still remaining relatively limited. So even now, what we're seeing is relatively uniform performance. Oddly enough, the convergence performance in V6 is slightly worse than V4, slightly worse, but constant. Eerily constant. Why? Well, as V6 becomes production, you have the same AS relationships. The average AS path length is now converging to about 4, much the same as V4. The behaviour of the distance vector protocol is the same, so much the same set of dynamics. So oddly enough, however you line up your business in peering, however you do exchange points, works. Fantastic. So this is all really, really good news. 70 seconds convergence, we're happy about this, yes? But is it a problem? Is it a problem? Well, the issue is routing doesn't happen way up in the cloud, it happens on routers, right? That's a router. And if any of you are old enough to remember a mainframe, that's a mainframe too. It's exactly the same architecture. There's this backplane, which is just a common bus, and there are these smart cards you put in. One card does the processing and management. There might be 1 or even 2 switch fabric cards. And there are these things called line interface cards. You just plug them in and it's a standard architecture. What's inside a line interface card? Well, over on one side is the media. The thing that talks photons, the thing that talks voltages, the thing that talks messy, analog stuff. And then there are a few digital signal processors, and that's where it gets interesting, because that analog stuff is kind of analog engineers' problems. The physical business breaks down that signal into packets that need to be switched. And at that point, you take the packet and pass it into the network layer, because the job of the router is not to collect packets, it's to get rid of them. So as soon as you've assembled the packet, the next task is to figure out, how do I get this packet out of me? And so you need to look up some kind of table to go, which interface needs to get this packet to get rid of it? And what you have normally is some kind of forwarding information block, a lookup bank, where you take the packet header and go, what am I meant to do with it? And it says, well, you might send it out the same interface card, or I'm sorry, that has to go out on a different interface card. If that's the case, you send it over into the backplane and send it off to some other interface card. But you've already made the decision how to get rid of it. And so the real interesting part of this is actually that block of memory just there, the TCAM or the DRAM. And that's the bit that I'm going to concentrate on. Because there's two ways of doing this. One is to use content addressable memory, and the other way is to use a simpler form of just basic lookup using a large tree, using a particular form of tree called a tree, which I'll explain in a slide or two. But you've got to do this at the rate at which packets arrive, because if you fall behind, you're going to drop packets. So you need fast memory. How does a TCAM work? TCAM's really, really easy. It's called TCAM because there are three states in memory. 1, 0, we know about those, and a third state called I don't give a shit. And that third state corresponds to the bit masks. So 192.0.0.0, the /16, has 16 bits of ones and zeros and 16 bits of don't care. At the /24 is represented as 24 bits of ones and zeros and 8 bits of don't care. You bang the address into this bank of memory, and as if by magic, one cycle later, out comes the right interface. Send it out that interface. Because it's content addressable memory, and what actually comes out is an index of how the packet needs to go out. One cycle, incredibly, incredibly clever. TCAM is brilliant stuff. But it's expensive. And if you're cheap, or whatever, you might try a different scheme using tree lookups. It's just basically a search tree. Is the first bit 1 or 0, go left or right? Is the second bit 1 or 0, go left or go right, etc. For V4, the maximum amount of comparisons is going to be 32, yes? 32 bits long. But if you're lucky, and it is luck, and the distribution of prefixes is just right, you might be able to make a decision within 8 cycles or 6 cycles, depending on the prefix you're looking up. So those are the two ways that happen inside routers. They're different. And the difference becomes your wallet and how much you want to pay. TCAM is really, really fast. Any kind of memory is actually going to be a bit slower. But the dollar per bit is a lot higher. There are more transistors in TCAM. You're going to need a lot more power. The density is worse. The physical size is larger. And it's a lot smaller. You can't do multi gigabits of TCAM easily or cheaply. Whereas DRAM, yes, you can. So those are the trade-offs router vendors go through. TCAM's a higher cost, but they're fixed performance, which is really, really good. And they scale linearly. ASICs with trees have a lower cost, but things become variable. And the memory efficiency depends on your algorithm that you're using. So if you're going to buy a router today, what should you buy? V4, 2 million entries. You need that much. V6, 1 million entries in TCAM. For trees, you're going to need about 100 megabits of memory. For V6, another 200. So if you're buying less than that today, not a good idea. It probably won't last as long as you need out there in the field. So fine, yeah, just buy more memory. And if it all turns horrible, what are you going to do? If we actually manage to outpace memory size, well, life isn't completely over. You can use fib compression. Gasp horror, you can actually unwield the evilness of MPLS. If you're really insane, you can go and do Lisp. I shouldn't say that. It's actually not a bad idea. It limits the amount of forwarding space you need to work on. Or if you really want to experiment on the dark side and do weird things with your routers, you can play with OpenFlow and SDN. But that would be evil. But again, as usual, it's not only size, it's speed. Because you've got to process a packet as fast as packets arrive. Now, originally, it was 10 megabit Ethernet. 64 bytes was the minimum packet. You had a packet every 64 microseconds. Yep. Now we're running 100 gigabit Ethernet. What's the minimum packet size? 64 bytes. I have no idea why, but that's the minimum packet size. So how has speed changed over years? Well, 1980s was 10 megabit. And it took quite some time for the data industry to actually fill up that wire. But inevitably, by the mid-90s we did, and the first 100 megabit standards came out around 1995 as standards. That's 150,000 minimum packets per second. Pretty soon after that, 1999 was 1 gigabit Ethernet. That's 1.5 million packets per second. And then we did 10 gigabit Ethernet in 2002, 15 million packets per second. And then there was nothing for a while, for almost 10 years, in fact, the next 8 years. And in 2010, there's 40 gig and 100 gig, 150 million packets per second. And the folk who are doing circuitry expect to be able to deliver something around a 1 terabit wire in 3 years. 1.5 billion packets per second. Whoa. So that's one packet every 0.67 of a nanosecond at 1 terabit speed. 0.67 of a nanosecond. How fast is memory? Well, that's a problem, because memory doesn't increase in speed according to Moore's law. Moore's law only said how big the chips are. It didn't talk about the cycle time. And in fact, the cycle speed of memory increases far more slowly than that. And the fastest memory we have today is DDR3 DRAM that operates between 9 and 15 nanoseconds per cycle. And if you really want to pay the big bucks, you do RLD DRAM, and that'll get you down to 1.9 nanoseconds. And that's the cutting edge of today. But you want to get to 0.67 of a nanosecond. You want to get below half, which is kind of interesting, because at some point, you're going to get into some real physical limitations here. Because scaling speed is actually far, far harder than scaling size. And I suspect that in the current round of router design, as we try and look at faster and faster circuitry, the real issue is the electronics aren't increasing in speed at the same time. What if we can't route a terabit? What if the electronics actually won't go at that speed by 2017? That's a real possibility. You cannot buy terabit hardware today. You cannot. It just does not exist. And my suspicion is that even in 2017, you can do the optics at a terabyte, but the packet rate will be nowhere near the maximal packet rate. So what are you going to do? When we found this problem in computers, just processing, the answer was really simple. We just went parallel. So these days, even in the fastest of the machines that come out from Intel, they gain their power by having multiple cores, 24 cores. It's basically everything becomes parallel. Do we do parallelism in routing in the internet? Yes and no. Equal cost multipathing, SDN, etc. Everything is sort of there if you're willing to experiment within an autonomous system. But what about in the interdomain space between autonomous systems? Is there any routing protocol that exploits parallelism? Nope, nothing. So is this whole path pinning, source-based routing, segment routing, going to have to come in simply because we can't make single-line best path routing protocols work at the speed, or sorry, the routers work at that speed? Are we going to be forced into parallelism because we just can't make the hardware work? Or as Matt Mathis, who's now working with Google, said, why are we sticking at 64 bytes of minimum packet size? If we'd have scaled the minimum packet size at the same way we scaled the clock, the minimum packet size in a gigabit network should be up around a few K, and for 1 terabit, the minimum packet should be 65K, damn it. Which, if that was the case, DNSSEC would be easy, right? Because then everything would sit inside a packet and you wouldn't have a problem. But I suspect it's really a fundamental issue right now, that the real problem that we're facing on the internet, and while we might have bad hair days in the future, is not the size of the problem. nor is even at the dynamic behaviour of BGP that's going to be the problem. It's actually clocking upwards to try and get terabit and multi-terabit systems working in a single physical channel that's going to be the problem. And at that point, I think when we take on the laws of physics, we might well lose, in which case we've really got to think long and hard about high-speed routing protocols. And I think that's where I ended up. So if you've got any questions, I'd be happy to try and punt them. Thank you.
Outstanding. Any questions? No. One from Tony, inevitably.
Tony Hayne. So spinning way back into your growth rates from IPv4, I realize the data is probably a bit hard to see at this point because we're relatively short into it, but have you had a chance to figure out if there's a significant impact from more specifics due to transfers? As the markets start taking over and V4 space gets more fragmented, can you pick that out yet and see what that growth rate looks like?
So there are some interesting observations, Tony. It's certainly true that since 2011, the number of more specifics has been slowly rising, but it's really slow because more specifics are about 50% of the routing table historically, and they're edging towards 51%.
No, I
fascinatingly,
understand that.
Fascinatingly, it's growing, but growing slightly. But the interesting thing is, when I look at what gets updated, the subject of updates, more specifics are 4 times more likely to be unstable than aggregates. So if we pump the network full of more specifics, do we change its dynamic property? Is this capping on the amount of updates some kind of artefact about aggregation? Sorry, Dean, I'm waving my arms. And we don't know this. We don't understand why BGP has been so well behaved. We don't understand why this sort of beast hasn't leapt out of the box. But it's something to do with aggregates and aggregate routing behaviour, but we don't quite know what.
Well, I agree, and to some degree, I think the instability you see in the more specifics is traffic engineering, SDN flavored mumble corp, right, where people are trying to manage flows, and that's part of that instability. It's where if you can get the data to pick out what's really traffic engineering versus what's market behavior growth, I think that would be an interesting number and impact your projections some.
Everybody should add a community called intent. And when they advertise a prefix, they should honestly write down why, and our problem would be solved.
Don't we already have the evil bit for that?
Yeah, it's the evil bit.
It's the Jeff Houston community.
You're right. Gee, thanks.
I'm here to gather data, please.
Yeah, please fill out this field. Yes, indeed. Thanks.
Yamanichi-san.
Hi, I'm Masato. Thank you very much for presentation, but your presentation scared me a little bit because you said some with ASIC DRAM architecture, some prefix has faster lookup speed than other prefixes, and it means we should have new address policy. So I don't want to. I really want to leave policy chair before that.
There was a paper in SIGCOMM in 2003, and it's in 2-point font down the bottom of that slide. So, go to this URL, go back to that slide and pick up the paper. Because it's a fascinating insight, it's done by computer scientists at the University of Berkeley, on the impact of what prefixes get announced and how that affects the performance of tree algorithms. And, if we did this just right, and I gave you 192.0.2. blah, 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 and I made sure that you got 193. And you just did this right, you could make the tree work really fast, right? In theory. In practice, yeah, right, that's never going to happen. But it is an issue, right, when you try and do these sort of sorting algorithms in the FIB, the big unknown is, what is the distribution of data that I have to sort and search through? And yes, that is kind of this variable on what we announce as prefixes.
Yeah, I mean, there are some other studies about the order that you learn the prefixes in, and even if you're building the same tree at the end state, if you build a big long branch and then
that would be a bad thing.
Exactly. So the order at which the BGP announcements come in and you build the tree, can have an impact as well.
This explains why, even though it's more expensive, a lot of router vendors like TCAM.
There you go. And on that note,
Thank you.
Thank you again. There we go. I went slightly over, but that is my prerogative as chair, and it was interesting, so I thought it was okay. What we will do now is have some morning tea. There's a very, very important session in here at 11 o'clock on consultation around the IANA transition. I would encourage all of you to come and actively participate in that. We, back in the meeting in Malaysia, the Apnic community said that they wanted more opportunities to engage and be engaged in these sorts of discussions. So the session in here at 11 o'clock is that opportunity for you. So definitely, come back, listen, get up to the mic and be engaged. So I'll see you all back in here at 11. Thank you very much.